Hello, in this video I'm going to talk a little about nuclear bombs. I mean, it's a controversial area, obviously, but you can't really go through the topic of nuclear physics without touching on nuclear bombs. I mean, this is, the forefront of science meeting ethics and a very sad and real impact upon the world. So, we might as well face up to the facts. So we need to know a little about how they work. I'm not going to go through all of the ethical implications behind them. Might save that for another day, but let's at least go through something about the different types of bombs that are out there. So really we're splitting these into two types. We've got the original ones, so our fission bombs. So for fission bombs, these are our atomic bombs. So our A bombs. So when you hear A bomb or atomic bomb, then that's referring to the original ones, the ones that were developed during the 1940s in that big rush towards the end of the Second World War, and then two of them were dropped, one in Hiroshima and one in Nagasaki in Japan. So these are essentially mini fission reactors. So you've got some enriched uranium or plutonium, and you need a critical mass of this stuff in order to get a chain reaction. So we're familiar with what chain reactions are like. But if you can get enough of this stuff in the right situations, then you're going to get a chain reaction happening. And this critical mass that people are after depends on things like the shape, the density, the temperature, the amount of the actual fission material that's available there, so the amount of fuel. So it's about setting up a structure where you can take the fuel in a non-critical state and then create critical mass. And this might be done by, say, having you get sort of gun mechanisms in some of them where you'll have two pieces and then one will get fired into the other one, and then that will create the whatever out of these: shape, density, temperature, fuel, whatever, in order to achieve critical mass. So you are literally firing it like a bullet, one into the other. Or you might go for one piece of subcritical material surrounded by explosives. You set off these explosives, and then that will compress the material that you've got. That then achieves critical mass, and then we're off on our chain reaction. So the challenge in these cases is to get enough fission before the whole bomb disintegrates. Because here you're already setting off an explosion around the material. So in that case, well, your bomb might start falling apart or whatever. You're certainly going to be doing some damage to it. Then we're starting off in both cases this chain reaction, which is releasing an enormous amount of energy. So how do you get enough chain reaction to release enough energy to have an effective bomb before the whole structure of the bomb is compromised and you're not getting any more energy release because the whole chain reaction stops because everything's disintegrated? So that is a challenge for, well, both these original A bombs, but also the ones that were built since, which are our, it's a mixture of fission and fusion. So these are the ones that are referred to as H bombs. So because we've got the fusion coming in from hydrogen, so H bombs, hydrogen bombs. The thermonuclear is another one that you'll hear on it. Thermonuclear bombs. What else do we have? 2-stage, 3-stage, or multi-stage. And the reason they're called that, so let's take a basic 2-stage one, which is where they started off. I think most of them are 2-stage weapons. So if you've got a 2-stage bomb, you start off with stage 1 is essentially a fission bomb. So it is another nuclear bomb So you're setting off a fission reaction. You're then using the the gamma rays that are coming out of the fission. So all of that energy that's coming out, this is the thermo bit in thermonuclear. So you're taking all of that energy and you're using that to go on to the second stage, which is fusion. And that is going to then heat a fusion reaction. So you've got all of that heat going in. It then fuses the hydrogen that you've got there, hence the H bomb. You then get another nuclear reaction, so that gets another massive release of energy. So you've already had energy come out here. Then you get more energy coming out here, plus you're getting all of these neutrons. You know, we've seen this before when we're getting fusion reactions of the neutrons coming out. And in fission for that matter. So sometimes you'll get a third stage where you'll then get a second fission stage kicked off with these neutrons. So, and you're getting energy from each stage. But yeah, these multi-stage ones, I mean, let's just focus on the 2-stage. So yeah, you're actually using a nuclear bomb in order to ignite another nuclear bomb as the trigger for the next one. So that's going on with these mega ones. And you can see the difference when you start looking at the yields of these things. So the yields as being the amount of energy that's being released in these things. So you've got, if you take the bomb that was given the name of Little Boy, that was the one that was dropped at Hiroshima in 1945. That was just a fission bomb, as they all were back then, and it had the equivalent power to around about 15,000 tons of TNT. So you've got that, which is around about 60 terajoules. So yeah, that is a lot of energy that's coming out of something like that. But then you take the sort of, the 2-stage ones that are active for although thankfully never used for the United States of America at the moment. So the B-83 thermonuclear bombs. Well, compared to this of the 15,000 tons, you've now got 800,000 tons of TNT equivalent. So that is a big jump up. That's about 3,300, so around about 3,300 terajoules. So you can see that is a massive increase. In the amount. That's like 60 times nearly the amount of energy that's being released there. The largest nuclear bomb that's ever been tested, the infamous Tsar bomb that was tested by the Soviet Union. That is just obscene. So this is now getting up to 210,000 terajoules. So it's just beyond comprehension how much energy would come out of that. So 50 million tons that we're looking here of TNT equivalent. So that's you compare to what we've got there. It's just insane the amount of energy that is coming out of this. You're looking at 3,000 times the amount there, if not more, 3,500 times the amount of energy coming out. He's hoping something like that, or something like any of them, never gets used again. But there you go. Like I say, I don't want to get into all the ethics of it all in here, but that gives you a breakdown of at least the 2 basic types that are going on here: the old style fission bombs, and now the more modern and far more powerful H bombs.